If we have two functions added together, two expressions that define functions added together, we looked at last time and saw that if we have the derivative, well, if we have f of x plus g of x, we can find the derivative of f of x, f prime of x, and the derivative of g of x, g prime of x, and all we have to do is add those together, and that gives us the derivative of the sum. Namely, the derivative of the sum equals the sum of the derivatives. We went there, we did that. Didn't prove it, but we looked at some examples and they seemed like they worked out okay. If we have a product, the derivative of f of x times g of x, we can find the derivative of f, we can find the derivative of g, and we could even multiply them together if we wanted to, but if we did, that would not give us the derivative of the product. The derivative of the product does not equal the product of the derivatives. A little bit more going on. We can kind of look at it here, but I will attempt kind of a proof of this. So maybe the proof first, and then we'll look at the definition. ddx of f of x times g of x. If we use the limit definition, this is the limit as delta x approaches 0 of, if we think of this as fg of x, if we were to evaluate fg at x plus delta x, the way we would do that is to say that's f of delta of x plus delta x times g of x plus delta x. So although it's kind of written like this, f of x times g of x, literally that's the product function. So if I want to evaluate the product function at x plus delta x, that's what it's going to look like. So let's scoot that up over there like that. So it's the limit of f of x plus delta x times g of x plus delta x minus f of x times g of x over delta x. Delta x approaches 0. Somehow we have to go to what we know. We know something about what's given. What's given is that f and g are both differentiable at x. So somehow we want to write this in terms of the difference quotient, where one would find the derivative of f of x, and the difference quotient where one would find the derivative of g of x. Went ahead in that direction. It won't take long. But there's kind of a slick technique for doing this that somebody a long time ago figured out. Limit as delta x approaches 0. Basically, I want to subtract something and then add that same something in between the two expressions in the numerator. It's going to be f of x plus delta x times g of x plus delta x. Going to subtract it, going to add it, and then I'll have minus f of x g of x. What to subtract, what to add? Well, I want it to be something that's going to involve one of these functions evaluated at x plus delta x, and the other function evaluated just at x. So let's see if this would make sense. We're going to go with f of x plus delta x times g of x. No, we need a g of x plus delta x. Sorry, reverse that. F of x, g of x plus delta x, plus f of x, g of x plus delta x. There we go.
You're adding and subtracting the same thing?
Yes. Subtract it, add it. So I'm not changing the value of the numerator. But what I can do is write this as two separate fractions. This is the limit as delta x approaches 0 of f of x plus delta x times g of x plus delta x minus f of x g of x plus delta x all over delta x. And if you'll believe along with me that these limits wind up existing, we can write this as the limit as delta x approaches 0 of f of x g of x plus delta x minus f of x g of x. That saves a step. Typically I write the sum of the fractions, and then I say the limit of the sum equals the sum of the limits, and then I write the sum of the limits. So this is the sum of the limits. Good things are supposed to happen. The good thing that happens here is that this has a g of x plus delta x and a g of x plus delta x in both expressions there. So I'm going to factor it out. This equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x times g of x plus delta x. Factoring the g of x plus delta x out of each factor in the numerator and then sliding it out next to that fraction. Plus the limit as delta x approaches 0, f of x, do the same thing except with the f of x, factor the f of x out of each of those two expressions in the numerator, and then multiply that by the fraction, g of x plus delta x minus g of x over delta x. Are you worried that we might not almost be done? Are you hoping that we're almost done? I certainly am. What do we know about this expression right here? If f were given, if f is differentiable at x. If f is differentiable at x, what do we know about that expression in red? That's equal to, well, it's the definition of the derivative. The derivative f prime of x. Yes, that's what that's equal to. Now, this limit, to save a little bit of space and definitely to save some time, because this gets wearisome really fast. It's been wearisome for a while. The limit of a product equals a product of the limits. So as delta x approaches 0, because g is continuous, how do I know g is continuous? I know g is continuous because g is differentiable. And a function must be continuous in order to be differentiable. So g is continuous. If delta x approaches 0, this expression inside here is approaching x. So the value of that expression is approaching g of x as a consequence of the fact that g is a continuous function. So times g of x when delta x approaches 0. Plus, over here, the limit of the product equals the product of the limits. So f of x is just plain old f of x, but the limit of g of x plus delta x minus g of x over delta x, that's g prime of x. All right, that's also found in the textbook if you want to refer back to that. Now, the product rule. The product rule can be written by considering these two functions and writing the sum of two expressions. Basically, you find the derivative of one of these functions and multiply by the other. You can find the derivative of the second function and multiply by the first. You can find the derivative of the first function multiplied by the second and add those two quantities together. This will give you the derivative of the product. Usually we like to say it in words because it's easier to remember. So the way I have it written here, it's the first times the derivative of the second plus the second times the derivative of the first. That is the product rule. The first function times the derivative of the second plus the second function times the derivative of the first. It looks like it could be a little bit of a pain, but it turns out to be considerably simpler than having to do something like this whenever we want to find the derivative of the product of two expressions. Let's see what specific function we look at first. In fact, if I'm trying to convince you that the product rule is a good idea, a good thing to do, example 1 is probably not the right example to use, because my suggestion is we do this, find the derivative 2 different ways. First, multiply it out, FOIL, and then use a combination of the power rule for each term and then the sum and difference rules. And that's going to be pretty simple. H of x equals, let's see, 3x times 2x squared equals 6x cubed. And you mind if I spell FOIL in an unconventional way? Maybe F-I-O-L? That'd be okay? Because I want to say minus 14x squared plus 15x minus 35. Does that look okay? The derivative of this should be a snap, yes? H prime of x equals, using the power rule, 18 x squared. I haven't graded that page of the test yet, but I'm confident that it went really, really well. Did y'all feel good about that page? Yes? All right. We'll find out. Minus 28x plus 15? Okay. So this is one way to find the derivative. It does not involve the product rule, and it was fairly simple. Now, the product rule is going to look more complicated than this. I'll admit it right now. But there are a lot of situations we're into where there's not a choice. We have to use the product rule, and we don't have this as an option. What we want to do is use the product rule and then compare and see if we get the same answer with something we know already works. All right, here goes. H prime of x. Maybe I should scoot it up here so that technically it doesn't look like it takes that much longer. It's going to be, and I'm going to use the DDX notation, it's going to be the first expression times the derivative of the second plus the second expression times the derivative of the first. The first times the derivative of the second, plus the second times the derivative of the first. F of x, g prime of x, plus g of x, f prime of x. That's what's going on here. Okay? So we calculate the derivatives, then we can simplify. H prime of x equals 3x minus 7. What's the derivative of 2x squared plus 5? 4x. And then 2x squared plus 5, what's the derivative of 3x minus 7? 3. Slope of that linear expression is 3. So we have the derivative, we just want to be able to compare it to the other one. So let's simplify, combine like terms. H prime of x, if I distribute the 4x across the parentheses, I get 12x squared minus 28x plus 6x squared plus 15. And if we combine the x squared terms, we get 18x squared minus 28x plus 15. So, two different methods, but the product rule gives us the same result as the power rule, sum and difference rules gave us, so we're going to trust it, even in those situations where the power rule, sum and difference rules really don't apply. Example 2, we actually could, and I don't know, perhaps should, use the product rule and the sum rule, not the product rule, the power rule and the sum rule. But I'm going to see if we can use the product rule and see how that works for us. So it's going to be f of x equals 3x to the fourth plus 4x times x to the 1/2. Honestly, if you distribute that x to the 1/2 across the parentheses, you will be done within a minute. It's going to take me maybe 5 minutes to finish this using the product rule. But let's see how it works out. F prime of x equals the first times the derivative of the second plus the second times the derivative of the first. So we delivered about to find those two derivatives. F prime of x equals 3x to the fourth plus 4x times, how do we take the derivative of x to the 1/2? 1/2 x to the negative 1/2. And we may need to deal with that negative exponent a little bit, but we'll wait on that. Plus x to the 1/2 times, just a polynomial here, 12x cubed plus 4. If we could just leave the final answer like that, then that would be nice enough. But there's simplifying to do. There'll be combining of like terms to do. In fact, I'm thinking it would be appropriate to factor out a common factor. Let me do one thing to the left. I see a common factor of x there and there. And I think I would like to factor out that x before we do anything else. So f prime of x equals,
We factor out a 4 out of the last.
we could factor out a 4 there. Yeah. Now I wonder what to do with the 1/2. Should I factor out the 1/2?
Doesn't that just make it negative 1/2? Doesn't that just mean it's x squared?
Well, the square root of x, or 1 over the square root of x.
Yeah.
Just want to make this as clean and neat as possible.
So it'd be 1 over the square root of 1/2 x.
Here's what I want to do. I want to say an x right there, 3x cubed plus 4, and the 1/2 x to the negative 1/2. I'm not sure if I want to factor out the 4. I know there's a common factor of 4 there, but since 4 is not a factor of this other expression, I'm thinking what's going to happen after this. Maybe hold off on the 4. X to the 1/2. I may change my mind in a minute. I want to factor f prime of x. See if this makes any sense at all. 1/2 x to the 1/2 times 3x cubed plus 4.
Negative 1/2? The 1/2? No, you add the x. X to the negative 1/2? You add
Did you
the x,
add
right?
or multiply?
You add the x.
See, what happened is that this x and this x to the negative 1/2, x to the 1 and x to the negative 1/2 got multiplied together. And I added the exponents to get positive 1/2. And I took the 1/2 out just because I didn't want the 1/2 inside the parentheses. It gets weirder, just wait. Plus 1/2 x to the 1/2, 24x cubed plus 8.
I'm okay with it.
24
multiply by 1/2 on the outside, and multiply by 2 on the inside.
Yeah, can you multiply the whole thing by 1/2 and on the big 12x to 12x?
Only on that side of the question.
Yeah.
See, basically it's this 1/2 times 2 times 12x cubed plus 4, where the 1/2 is red and the 2 is red. Why the 1/2? Well, I've got this 1/2 over here. I've got that 1/2. And I just want a matching 1/2. If they would match, I could factor a 1/2 out of both of them. That's what I want to do. So there's not a 1/2, so I put one there. And I can't just go putting a 1/2 just because I feel like it. I have to account for that, have to compensate for that by putting a 2. So effectively, I multiply by 1/2 and then I multiply by 2 over there. And that's like multiplying by 2 halves, which is like multiplying by 1, which is like doing nothing at all. I do it because I need to. All right. So with that extra step thrown in, see if it makes sense to say f prime of x equals 1/2 x to the 1/2. I'm copying and pasting here. 3x cubed plus 4 plus 1/2 x to the 1/2. 24x cubed plus 8. 1/2 comes outside, 2 gets distributed across the parentheses. So f prime of x is equal to 1/2 x to the 1/2 times 3x cubed plus 4 plus 24x cubed plus 8. And we can add them. 27x cubed plus 12. And then factor 3 out of that. Can I catch it all? Maybe. So f prime of x equals 1/2 x to the 1/2 times 27x cubed plus 12. Should I factor out the 3? I mean, I factored out everything else. F prime of x equals 3 over 2, x to the 1/2 times 9x cubed plus 4. How would this have gone had we just used the power rule? I'm thinking it wouldn't have taken as long. F of x equals 3x to the 4th plus 4x times x to the 1/2. F of x equals 3x to the 4.5, that would be 9 halves, plus 4x to the 1.5, that's 3 halves. So f prime of x, 9 halves times 3 is 27 halves. Subtract 1 from the 9 halves and you get 7 halves. Plus, what's 4 times 3 halves? 6. 6x to the 1/2. I suppose you could call that done because that looks nice enough. Or you could factor out you could factor out 3 halves x to the 1/2. And I think you have 9x cubed right there plus 4. Woo. Wow. Clearly my objective here is not to sell you on the efficiency of the product rule. Because that the product rule itself would have taken way longer than absolutely necessary. In some cases, you just have to look at it and say, you know, a faster way to go would be not to use the product rule, or when we get to the quotient rule, not to use the quotient rule.
What if you would have factored the x out and you would just multiply the whole thing before you start factoring, like the first step?
Factor the x out here.
If you would not factor the x out, but if you just multiply it altogether. Like when you got the first step, and you start multiplying, factoring the x.
Well, it would have looked like this right here. Yeah, basically, I multiplied the x to the 1/2 through there, and then we didn't have a product anymore. Yeah, that's how it would have looked. Whew. Let's look at the quotient rule. Quotient rule, I will not attempt to prove this. No way, no how. That was enough suffering involving the proof of the product rule. But I do want to consider the similarity between this and the product rule. Quotient rule looks like this. If we're taking the derivative of a quotient, a fraction, the thing to keep in mind is the first thing to do is take the expression in the denominator, write it in the denominator, and square it. No derivative, just whatever's in the denominator, write it in the denominator and square it. While we're thinking about it, write it down again, g of x. And then consider what goes on in the product rule. In the product rule, you've got those two expressions, and each one has one of the functions and the derivative of the other. So that's kind of what goes on in the numerator of the quotient rule. You've got the function g, and you've got the derivative of the other function f. Then you've got the function f, and you've got the derivative of the other function g. So if you can start with g, I think the rest of it will just fall into place. The denominator times the derivative of the numerator, and then there's a minus. Product rule has plus. Quotient rule has a minus. But once you put the minus, it's then the numerator times the derivative of the denominator. So there are various different ways of memorizing mnemonic devices that you can come up with for memorizing the quotient rule, but TA that I had when I took the class kind of used that, and that I found to be fairly helpful. Let's look at example 3. Now at this point, happily, or maybe not so happily, there's not an alternative to the quotient rule, because there's really not a better way to write this. We can't just distribute something across the parentheses and use the sum rule, power rule. This is a quotient. We're kind of stuck with this quotient. So to find the derivative, f prime of x, we'll just prepare a great big fraction, and we'll begin with the denominator, and we'll put that in the denominator, and we will square it. Whatever's in the denominator, put it in the denominator, square it. While we're thinking about it, write it down again. X squared plus 1. What that does is it reminds me not to take the derivative of the x squared plus 1 right there. I would think it would be easy to say, well, is it g in the first part, or is it g prime? You know, is it gf prime or g prime f? Well, if you remember what goes first is what you just wrote down and squared in the denominator, it helps to clear that up. Now, multiply that by the derivative of the numerator, and then put a minus, because the quotient rule has a minus. Then, since in this first expression it was the denominator times the derivative of the numerator, we've got to reverse that. It's going to be the numerator, 2x minus 3, times the derivative of the denominator. Just like that. Once you have all that written down, it's just a matter of differentiating, simplifying, combining like terms, maybe simplifying some more. So we take the derivative, f prime of x equals, well, the derivative of 2x minus 3 is just 2. Slope of that linear expression, minus 2x minus 3, derivative of x squared plus 1, just 2x, using the power rule on the x squared. Derivative of 1 is 0, so that doesn't contribute anything to the derivative. And we still have x squared plus 1 quantity squared in the denominator. And we have an expression to simplify in the numerator. Give myself a little bit more room down below and then off to the right hand side. F prime of x equals 2x squared plus 2 minus, a little tricky here, but we can handle this. It's minus whatever 2x times 2x is. And then it ought to be plus whatever 3 times 2x is. Maybe it'd be good to think of it as negative 2x times negative 3. It's going to be plus 6x. Everyone feel good about plus 6x there? Yeah. So x squared plus 1, quantity squared in the denominator. Just about there, I think. Combine the x squared terms to get 6x squared. No. Opposite signs there. Negative 2x squared. Negative 2x squared plus 6x plus 2 all over x squared plus 1, quantity squared. Now I suppose if we could factor the numerator in such a way that there was a factor common to something in the denominator and we could reduce it, that would be a good thing. Ordinarily I might not worry about factoring the numerator, but maybe factor out the negative 2. Inside we get x squared minus 3x minus 1. I believe that trinomial is prime. So it would look like this.
So that's the answer.
That is the final answer, yes. Now we don't want to lose sight of what we're doing here. If we had this original graph and we had a point, we want to know what's the slope of the tangent line at that particular point, then we take that x-coordinate and evaluate this expression, and that would give us the slope of the tangent line to the original graph at that particular point. There it is. Now example 4. Examples 1 and 2. We use the product rule and then we use other rules, and we found that the other rules seem to be way simpler than the product rule. Here's a case where we could use the quotient rule, but there's a nice alternative to the quotient rule because the denominator is a monomial. If you have a fraction and the denominator is a monomial, there will often be a real nice alternative to the quotient rule. Just take the expression and write it as the sum of 3 fractions, each of which is in lowest terms. Maybe the first step or two of the quotient rule will be in order, though. F prime of x equals, take the denominator, write it in the denominator, and square it. While we're thinking about that x squared, write it down again. And then multiply by the derivative of the numerator. Since the first part up there was the denominator times the derivative of the numerator, you write the minus, and then you have the numerator times the derivative of the denominator. That looks like that could take a while. Let's get back to that later. Let's try over here. F of x could be rewritten as 3x to the 4th over x squared plus 2x squared over x squared plus 5 over x squared. right? The sum of those three fractions, they've got a common denominator. If you wanted to add those three fractions, you'd just put the denominator x squared and add the numerators, and you'd get what we started with. Simplify each one. Now, if we had x squared plus 5 in each denominator, we wouldn't be able to do this at all. It just wouldn't simplify. It wouldn't be nice. It wouldn't be helpful. But just plain old x squared does this. 3x squared plus 2 plus 5x to the negative 2. Now we can take the derivative. This is nice, huh? F prime of x equals 6x plus 0 minus 10x to the negative 3. And then it just depends on how much more we want to do. Do we like negative exponents? Maybe we don't. If we don't like negative exponents, then it's 6x minus 10 over x cubed. Do we like a single fraction or the difference of these two expressions? Maybe we're okay with the difference of these two expressions. If so, we just leave it like this. Now, eventually we would get to an equivalent expression if we continue with that. I don't know if I want to, though. I think maybe just leave it to you and say, at some point, the next lazy Sunday afternoon you run into, go back to that, give that a try, and see if you can make it look like what we got there. Sometimes the quotient rule is not the way to go. If there is a constructive alternative, maybe go with the alternative. All right. Didn't have a lot of trigonometry on the last test. There'll be more of it on this upcoming test because we have a little bit more because we took the derivative of sine x and cosine x using the definition. Once we have derivative sine x and derivative cosine x to work with, we can use the quotient rule to come up with the derivatives of the other four. How can you write tangent x in terms of sines and cosines? Sine x over cosine x. So this looks like a job for the quotient rule. We have a quotient of two expressions, each of whose derivatives. So here it goes. It's gonna be. What do we do first with the quotient rule? How do we do this? Take the cosine x and square it. Yes, cosine x. If you want to go ahead and say cosine squared x, I'll write that at the next step. But take the cosine x, put in the denominator, square it, just like that. While we're thinking about cosine x, write it down again. And then multiply by the derivative of that other function that we're having to deal with in this example, the sine x. Put the minus. And since we just wrote the denominator times the derivative of the numerator, now we want to write the numerator times the derivative of the denominator. Just like that. Now let's recall what those derivatives actually were. Off here in the corner somewhere, we want to remind ourselves the derivative of sine x equals, anybody remember?
Negative cosine.
Well, it's one of those. It's actually just plain old cosine x if we go in this direction. And if we want to go back, that's where that negative sign comes into play. Derivative of cosine x is negative sine x. All right. So as we simplify this, we'll keep this in mind. So we get cosine x times negative cosine x minus sine x times, oh my goodness, wow, they pay me real money to teach this course too. Not a whole lot, but I mean they do. Derivative of sine x is cosine x. I just got through saying that. Derivative of cosine x is negative sine x. Don't know where that came from. All over cosine squared x.
So the top's going to be 1?
Well, the top is going to be 1. It sure is. Look at that. Cosine squared x plus sine squared x over cosine squared x. And our familiar Pythagorean identity, that is 1 indeed, over cosine squared x. So we can write this in terms of secant. Secant squared x, cosine x and secant x are reciprocals of each other. So 1 over cosine squared x equals secant squared x. Mark it down. Probably a dozen or more times between now and the end of the course you'll be called upon to take the derivative of tangent x. And you just want to have it memorized. Secant squared x, that's what it is. Derivative of tangent x is secant squared x. So all 6 of the trig functions you want to have the derivatives memorized and make sure you can recall those. Now the derivative of cotangent x is similar. I'm not sure if I want to take the time to go through all that. Maybe just leave it as an exercise for you, but I will go ahead and say it's equal to negative. I would just say, someone have a guess what it might be.
It's going to be cos. Is it secant? You flipping it though. Oh, cosecant.
It's going to be that. Yeah, derivative of tangent x, secant squared x. Derivative of cotangent x is going to be, you would think maybe just cosecant squared x, but it turns out to be negative cosecant squared x. What happens, let's see, what happens down here is that in the numerator,
You think you just flip it because they're the opposites? It doesn't turn negative. Like you have the sine x and the negative sine x, it's going to be in different spots.
I feel like I should actually work this out.
Yeah.
We're going to end up with a negative sine squared x minus cosine squared x in the numerator, and we'll factor out the negative sign, and then we'll have negative 1 there. And in the denominator, it will be sine squared x. That's the way it shakes out. I don't know how obvious that is, though. So let me just go through it quickly. It'll be, if I write this as ddx of cosine x over sine x, it looks like this. You have the sine squared x in the denominator, and then it's sine x times derivative of cosine x minus cosine x times the derivative of sine x, and then it's sine x times negative sine x minus cosine x times cosine x over sine squared x. So there you go. Negative sine squared x minus cosine squared x over sine squared x. If you factor out the negative sign, you get 1 on the inside. So negative 1 over sine squared x, and that's negative cosecant squared x. It'll be kind of a recurring thing. We take the derivative of a particular function. The derivative of the cofunction will be similar, but we'll have a negative sign associated with it.
Are we going to do something like this on the test?
As far as showing this, I think these would be nice test questions, although typically, no, I would like you to memorize. I would like you to memorize the derivatives of the 6 trig functions, and then maybe find the derivative of, some mashed up combination of trig functions rather than just a single trig function. Question?
On the test, would you give us the equation for the product rule, or would we have to memorize that?
Definitely want to memorize that. Definitely want to memorize the product rule and the quotient rule and be able to use those. But if you do all those homework problems, it will be so etched in your memory as you wouldn't be able to forget it if you wanted to. And you might want to, I don't know. Derivative of secant x. We want to write it in terms of what we know. Maybe it's tangent, or maybe it has something to do with tangent. Seems like it does have something to do with tangent. Let's write this in terms, let's write secant x in terms of a function whose derivative we already know. How do you write secant x in terms of either sine, cosine, or what else do we know? We know, yeah, how about that? 1 over cosine. Like that.
So does that make it 1 over negative sine?
Well, what will have to happen is we'll have to use the quotient rule. Have to use the quotient rule here. Where 1 is nice. Derivative of 1 won't be any trouble. But the whole framework here is we've got a quotient of two functions. The numerator is 1, the denominator is cosine x, and we just fit it into the template for using the quotient rule. So we take what's in the denominator, and we write it in the denominator and square it. Cosine x. Square that. While we're thinking about it, write it down again. But then multiply by the derivative of 1. Okay, so that part of the expression is going to go away in a minute. Minus 1 times the derivative of cosine x. And we'll see how this shakes out. Of course, the derivative of 1 is 0. We'll write that down. Cosine x times 0 minus 1 times derivative of cosine x is negative sine x all over cosine squared x. So the numerator ends up being what? Well, I heard a lot of stuff there. 0 minus negative sine x? So just sine x over cosine squared x. This is one way. One could write the derivative of secant x. There are many other ways one could write the derivative of secant x. It's just not the most popular way. When you look in probably the back of the textbook, front of the textbook, wherever all these derivatives are listed, derivative of secant x equals blah, it's not going to say sine x over cosine squared x. It's going to be secant x tangent x, because the idea is it's better without a fraction. Better without a fraction. So although it may not be obvious why one would want to do this, we could write this as 1 over cosine x times sine x over cosine x. The idea being, let's see if we could write it so that it doesn't involve a fraction. And then 1 over cosine x is secant x. And better yet, where it does involve the original function secant x that we're trying to differentiate, times tangent x. So derivative of secant x times tangent x. Reasonably easy to remember. If we can remember that, I'm going to try to resist the temptation to show all the work for this one. ddx of cosecant x. Real close to that. Cosecant x, cotangent x, negative. Yes, would be negative. So if you can remember one of these, maybe you can remember the other one. It's a product of those cofunctions, but it does end up that sign gets flipped. So somewhere, note card, all 6 of those derivatives, or 6 different note cards, however you like to study that sort of thing. Definitely want to memorize those early and often. And then we use product rule, quotient rule as needed when we have different combinations of trig functions mashed together like these. So example 6, we've got a product, x times sine x. Really no way to do this other than using the product rule, no nicer way than the product rule. It's been a long time. It's been, what, almost an hour since we used the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. So it's been even longer since we used that dy dx notation. But dy dx, the derivative of y with respect to x, means the same thing as f prime of x. Same thing, it's just different notation. Dy dx equals the first times the derivative of the second plus the second times the derivative of the first. And then we simplify. Well, differentiate and simplify. Dy dx equals x times cosine x plus sine x times 1. I wish I had a real neat, clean way of writing this, but really don't. That's basically it. Dy dx equals x cosine x plus sine x.
Now this isn't something we need to remember, right?
That's right. This is just remember the derivative of sine x, and then you can calculate this. 2 sine x cosine x. Now this is a what? Double angle formula? Not this, but you could write it as the sine of 2x. We haven't done the chain rule yet. When we do the chain rule, the next section, it will enable us to differentiate sine of 2x, and then we can come back and compare to this. But for now, dy dx equals. Now the 2 you could leave on the extreme outside if you want to, and just deal with sine x cosine x, or it wouldn't be too tough just to associate the 2 with the sine x. I'm going to associate the 2 with the sine x. Either way, we're using the constant multiple rule, but I'm going to think of this as 2 sine x times cosine x. You can do it a little bit differently if you'd want to. I'm going to do it like that. So it's the first times the derivative of the second plus the second times the derivative of the first. There is an extended version of the product rule where it's the product of FGH, and it just gets it's interesting how it works out, but we usually don't need the souped up version of the product rule. Just this, and we can use it repeatedly if necessary. 2 sine x times negative sine x plus cosine x times, and here I have to be a little bit careful, it's the derivative of 2 sine x. So using the constant multiple rule, that would be 2 times whatever the derivative of sine x is. So it's 2 cosine x. Like that. Dy dx equals negative 2 sine squared x plus 2 cosine squared x. And there are various different ways to rewrite that, but we just can't get a sine squared x plus cosine squared x in there. It just doesn't work itself out. You could actually rewrite this in terms of a double angle formula for cosine, but we won't. We'll just leave it like that.
So there's no way you can make it so it be for one.
That's right, because they have opposite signs, right? There's a formula for cosine 2x. Cosine 2x equals cosine squared x minus sine squared x, and there are a couple other variations of that. We can make it look like one of those, but we just can't get it to equal 1. Higher order derivatives. Higher order derivatives. As soon as we get to the point where we feel good about taking a derivative, we realize that when we have a function, we take the derivative of that function, we get a function. And the new function that we get, the derivative, f prime of x, we might ask ourselves, well,
If we take the derivative of the derivative.
what do we take the derivative of the derivative? What then? Well, in some cases, it's interesting, and it can tell us some things about the original function, the derivative of the derivative. So we do that, and when we take the derivative of the derivative, we call it the second derivative. And we have a lot of different notation for the second derivative. Basically, if we have f of x equals, and I think I want to go ahead and look at this. Is it in terms of t? No, there's one in terms of x, there's one in terms of t. I'll let it alone. Well, let's make one up. F of x equals x squared plus 5x plus 7. F prime of x would be one way to say 2x plus 5 for the derivative. And then if we want the derivative of that, we would denote that f double prime of x, and that would just be 2. We call it the second derivative of the original function f.
What do you need it for?
Well, what it tells us is, well, what the first derivative tells us is the rate at which the original function is changing with respect to the independent variable x. What the second derivative tells us, it tells us the rate at which the first derivative is changing with respect to x.
So on the third one, it's just 0?
In this case, if you start with a polynomial and you take enough derivatives, n plus 1 basically, where n is the degree, you kill it. Yeah. So
does any function ultimately end up at 0 somehow?
every polynomial function, if you take enough derivatives, you eventually get 0. Other types of functions, you don't. I mean, there's some interesting things that happen now that you mention it.
Divided by 0.
F of x equals sine x. Maybe I should call it something else. G of x. What is g prime of x? Cosine x. What then would be g double prime of x? Negative sine x. How about g triple prime of x? Negative cosine of x. And one more. At some point, we reach a point where we put enough primes. And so we denote the fourth derivative. We put a little 4 in parentheses. If we don't use the parentheses, it means actually g to the fourth power, which means something else. But the fourth derivative
Can we not use our big rolls or no?
is it's better just to use the regular Arabic numerals. Yeah. What's the derivative of negative cosine x? Sine x.
There's your period.
There we go. So, in some cases where sines and cosines are involved, we can take enough derivatives and actually get back where we started. So we're never going to zero this one out, obviously. We'll just, every fourth derivative is going to be back to sine x. When we look at rectilinear motion, the second derivative is going to be the acceleration, which relates back to the original function. And when we look at curve sketching, we'll see that the shape of the graph will be indicated by the sign of the second derivative. We'll see that graphs that curve upward will curve upward on intervals where the second derivative is positive, and we'll see that graphs that curve downward will curve downward on intervals where the second derivative is negative. So the sign of the second derivative is going to tell us some things about the shape of the graph. Third derivative, fourth derivative, we really won't look at key features of the original function that they may give us. They're a little bit too far removed from the original, but the first and second derivative will be important to us. Other notation. We've seen different notation for the first derivative. There was f prime of x. There was also dy dx. if we take additional derivatives, of course with the f we put an additional prime on there. For the dy dx notation, you see the appearance of these 2's. We read that d2y dx2 for the second derivative of y with respect to x. And I'm gonna write this out, and we'll see if it makes sense why the 2's are positioned like they are. If we had, suppose, I guess I should write y equals x squared plus 5x plus 7, dy dx equals 2x plus 5. Now, if I differentiate both sides with respect to x, differentiate both sides with respect to x, d dx of dy dx equals d dx of 2x plus 5. Use the differential operator, d dx. On the left, see if visually it doesn't make at least a little sense to say d2y dx2. A little bit?
When you put the dx in parentheses on?
Well, kind of. Maybe that's what was done a few centuries ago, and they just got tired of the parentheses. It would seem like that might be the thing to do, but this is the notation that's kind of shaken out of it. And then equals 2. So d2y dx2, and then you see where the 3 appears and the 4 appears and the n appears. No need for parentheses around the n in this particular notation, because there's no way to confuse that with something raised to the nth power. So you still need the parentheses around this n here, because that could mean f raised to the nth power, but not with the differential notation like that. The other notation, we won't use this notation all that much in this class. In differential equations, you would run into this notation a little bit in Calc 3, that notation. Particularly when there might be, it might be particularly important which variable you're differentiating with respect to. Okay, a couple quick examples here before we see if we can say what we can say about the chain rule. Example 7. A little bit about the rectilinear motion. The position function, s of t gives the height in feet of an arrow t seconds after being fired. The science folks would not be pleased with me for using feet rather than meters, but I just like the number for acceleration due to gravity, 32 feet per second rather than what, 9.8 meters per second squared. Yeah. So I use feet just because the number's nicer. S prime of t equals negative 32 t plus 128. The rate at which the position is changing is the velocity. The instantaneous rate at which the position is changing is the velocity. So we'll call this v of t. V of t equals negative 32 times t plus 128. Now in this, the assumption is that the initial velocity is 128 feet per second, positive, the arrow's headed up. So if the initial velocity is 128 feet per second, and gravity, I guess we should say the acceleration due to gravity is negative, gravity is reducing that by 32 feet per second each second. Let a second tick by, and then it's going to be down to 96 feet per second. Let another second tick by, and it's going to be down to 64 feet per second. So after 4 seconds, the velocity is 0. And that's what happens right there. At this point, the velocity, this is the position function, so the velocity is the slope of the tangent line. And when the velocity is 0, the tangent line is horizontal. It's going to be big in the coming weeks to be able to find the point where the tangent line is horizontal. That's where the graph stops increasing, starts increasing, or starts decreasing, or vice versa. So we'll look
vertical velocity, right?
Yeah, vertical, just straight up, straight down, just in the one dimension there.
Okay.
Just the height. So we're not looking at like breaking it down into components or that. We're just this is the time is the that should be a t there. Time is the horizontal component there. All right. So that's the velocity function, and if we take v prime of t, that's just going to be negative 32. And we can regard that as the acceleration function. So we're looking at uniform acceleration, or constant acceleration. The particle is constantly having its velocity change at the rate of negative 32 feet per second per second. Don't have the graph of the velocity function, but I guess what I could say is this. I mentioned earlier that when the graph is curved downward, that's on intervals where the second derivative is negative. Well, the second derivative is negative throughout this entire interval from where the arrow is shot until it hits the ground, and that's indicated by the fact that the acceleration, the second derivative, is negative throughout that interval. Okay. More about rectilinear motion in the future. Example 8. Mentioned if we take enough derivatives of a polynomial function, we eventually kill it. Basically, it takes n plus 1, where n is the degree. So we're going to take 6 derivatives of this 5th degree polynomial function, thereby killing it. F prime of x equals 5x to the 4th plus 4x cubed plus 3x squared plus 2x plus 1. F double prime of x equals 20x cubed plus 12x squared plus 6x plus 2. F triple prime of x equals 60x squared plus 24x plus 6. It gets I guess faster because we have fewer terms to deal with each time, one fewer. Fourth derivative with respect to x is 120x plus 24. Fifth derivative is 120. And the sixth derivative, of course, is 0. There we go. Oh, there's a name for the, as it relates to the rectilinear motion, for the third derivative, a prime of t. It would be 0 in this case for the uniform acceleration due to gravity. When we take the fourth derivative, and it starts with a j. Position function, velocity function, acceleration function, the derivative of the acceleration, the rate at which the acceleration is changing. Basically, you're exerting, instead of exerting a constant net force, it's a force that's maybe increasing. It's called the jerk. It really is. You'll find this. Yeah. Chain rule. Let's see what we can say about the chain rule in the few moments that we have left.
And J prime was 0, right?
What's
On the
that?
last one, too.
J prime was equal to 0. Hopefully I put 0. Did I put 0? We'll soon see.
J prime.
Oh, J prime, yes. All subsequent derivatives.
Okay.
would equal 0. But j itself was a prime of 0. I guess I should say that.
Could it be different than 0?
What, j? Well, if the acceleration, just imagine that there's a particle and there's a force acting on it, and the force is changing. Yeah, the force is changing. It's a variable force. So with acceleration, except for the fact that the distance between the object and the center of the Earth is changing, and thus, other than that, if it's a real noticeable change, then yeah, the object could feel like it's being jerked around rather than smoothly accelerating. So in that case, j itself might j prime might not be 0.
What were you calling the jerk?
What was I calling it?
J
is a prime of x, or a prime of t.
And so then J is known as the jerk.
The jerk, yes. Yeah, I guess I did not really clarify that. J of t equals a prime of t, and j itself is the jerk function. The chain rule. Okay. If we could write a function in terms of the product of two functions, each of whose derivatives we know how to find. It would say a function is f of x times g of x, and we know how to find the derivative of f of x. Maybe we know it, we've memorized it, maybe we know the derivative of g of x. We can find the derivative of f of x times g of x using the product rule. If we can write a function as an expression divided by an expression, and each of those expressions we know how to find the derivative of, we can find the derivative of our function using the quotient rule. Chain rule, there's a little bit more going on. If we can write a function or an expression in terms of the composition of two functions, f and g, each of whose derivatives we know how to find, we can find the derivative of that function or expression using the chain rule. Basically, there are two functions, f and g, and the function that we have can be written, let's see, h of x equals f of g of x. If we know how to find the derivative of f and we know how to find the derivative of g, we can express the derivative of h in terms of the functions f and g and their derivatives. That's enough. So the idea is we look at a function and it just looks awful, but if somehow we can write it as the composition of simpler functions, each of whose derivatives we know how to find, then the chain rule will enable us to differentiate that function. So there are a couple of ways to write this. One involves the introduction of another variable, u. And sometimes it's good to have a fundamental definition when the simplification doesn't seem to work, some place to go back and say, okay, what is it that we're talking about? What's the original definition of the chain rule? So imagine we have y equals f of g of x. What we want to do, in place of g of x, if that's too complicated, just substitute the variable u. Let u equal g of x. So we're looking at the function y equals f of u. Looking at that function. Well, we want to write dy dx in terms of the derivative of y with respect to u, but we also have this other relationship, u in terms of x. So we can calculate the derivative of u with respect to x. The chain rule says the derivative of y with respect to x, basically this original expression that we have, is equal to the derivative of y with respect to u times the derivative of u with respect to x. And I claim this is fairly easy to memorize once that you understand really what it's saying, because it sort of resembles the notation that we use for multiplying fractions. not really multiplying fractions here, but it sort of looks like we are. And if you could scratch out those du's, you get dy dx on the left. Not technically what we want to do, but notationally it sort of looks like that. So I would have, before I write this in terms of just plain old x, I want to see if we can use the dy du and the du dx to evaluate a derivative using the chain rule. So I'm going to scroll down and look at this first example. Just using the definition, then we'll try to make sense out of it. The function u is to be thought of as the inside function. Basically, composition of functions means you evaluate one function and you get an answer, and you take that answer and then evaluate the next function at that answer. That's how composition works. So the inside function, the first one that you would evaluate is the u. So we let u equal 8x squared minus 2x plus 3. Because we know how to find the derivative of 8x squared minus 2x plus 3. That's no trouble. We might not want to raise that to the fourth power. That's a real pain to raise a trinomial to the third power and multiply all that out. But we know how to do this. Then y equals u to the fourth power. If we pick all that stuff up out of the parentheses and put a u in there, then that's u to the fourth power. So if we have u in terms of x and y in terms of u, we can find du dx, and we can also find dy du. Is this the first time we've talked about dy du? Independent variable is different, but it's the same idea. The derivative of y with respect to u. So this is going to be 16x minus 2. And dy du is 4u cubed. So we write the formula. Dy dx equals dy du times du dx, and then we multiply. Dy dx equals 4u cubed times the quantity 16x minus 2. Guess I don't need the dot there if I'm going to use parentheses. 16x minus 2. Except that our final answer doesn't need to have any u's in it. The original expression didn't have any u's in it, so our final answer doesn't even have any u's. The u is just something that we made up to make the calculation simpler. So the final answer, substitute that expression back for u. So dy dx is going to be 4 times 8x squared minus 2x plus 3 to the third power times 16x minus 2. We can simplify that further. It just gets tedious from here. You could factor a 2 out of the 16x minus 2. Then you take that 2 and multiply it by the 4 out in front. But as far as the substance of this, we've calculated the derivative and almost simplified it completely. Now, the thing I guess I should point out here, if we didn't know about the chain rule and we're just looking at this expression, we might just think power rule. Because what we have is an expression raised to a power. We've got 8x squared minus 2x plus 3 quantity to the fourth power. And it would seem like just use the power rule. Take that 4, bring it out in front, reduce the exponent by 1, and if we did that, we would get, different color, like that, we would get this. That's what we'd get. We'd be off by, a bit. There's the 16x minus 2 that we'd have to contend with. But where does the 16x minus 2 come from? How could you look at this expression right here and come up with 16x minus 2 as the derivative of that? So the chain rule is going to talk to us for the rest of the semester. For the rest of the semester, you're going to hear me say, and the chain rule says, multiply by the derivative of what's inside the parentheses. That's what the chain rule is going to tell us. Because you take the derivative kind of like you would expect to. The derivative is something raised to a power. You take that power, bring it out front, reduce the exponent by 1. But the chain rule says multiply by the derivative of what's inside the parentheses. Basically, multiply by du dx, the derivative of the inside function. And when we do that, we'll have it. So in practice, we won't write the u, and we won't calculate the dy, du, and the du dx separately. We'll just deal with this in terms of f's and g's and x's, because it takes too long to write all this down. But that's kind of what's going on. We take the derivative of the outside function, and then we multiply by the derivative of what's inside the parentheses. Is it time for example 2? We can just try example 2 there. The so-called generalized derivative formula without looking at the specific nuts and bolts of the generalized derivative formula. Dy dx equals, well, this looks just like the one we just worked.
3 times the whole formula. And then the derivative.
Just like that. So that's what we'll do with the chain rule in practice. We want to think inside function versus outside function. There'll be a trig function down there in a little bit. If we want to find the derivative of, say, the sine of x squared plus 7x, what's the inside function? X squared plus 7x, and the outside function is sine. Now we know how to find the derivative of sine. The derivative of sine is cosine. Now I said it once and you're going to remember it wrong forever. Cosine x. So the derivative of the sine of something is, I'm going to say it like this, it's the cosine of that something times the derivative of what's inside the parentheses. So times the derivative of that something, 2x plus 7. And usually we'll put the 2x plus 7 in front so it doesn't look like we're trying to take the cosine of that. So it would look like that. So it's the cosine of that something times the derivative of that something. And we'll do that with the chain rule.